Hi everyone. In this video I will be demonstrating how to perform a three-level multi-level model using SPSS version 28. And the data and the example are based off of a presentation by Hawks et al. In their 2017 book, Multi-Level Analysis Techniques and Applications. So in their presentation, basically in chapter 2, they kind of walk you through a 2-level and a 3-level model. So we're pivoting off of that 3-level example, but they don't really walk you through how to perform the analysis using SPSS or any other type of program. They end up essentially giving a lot of the results in table 2.5. And so what I thought I would do in this video presentation is walk you through steps for how to obtain the results that are given in table 2.5 and also kind of comment on the results that we generate as we go along. I do want to mention that I'm saving a lot of the more complex discussion and about the results and the models that we're working with for a PowerPoint presentation that I put together on this particular example, and you can actually obtain a copy of that PowerPoint by following the link that's provided underneath the video description. I'll be honest, there's not a whole lot of demonstrations out there that I've seen with respect to three-level multi-level models, and my guess is it's because it's just really darn hard to explain results very simply and without making a lot of errors. So I'm kind of leaving it to the written form, if you will, within that PowerPoint to kind of provide a lot of the elaborations. So again, you can obtain a copy of that PowerPoint by following a link that's provided underneath the video description. You'll also find under the video description a link to the SPSS data file that I'll be working from. So before we open up SPSS and begin running our analyses, let's talk a little bit about the example and the data. So the data set is comprised of data on nurses who are working within wards, and those wards are nested within hospitals. So there's 25 hospitals that are represented, and within those hospitals you have wards, and within those wards you have nurses. So the purpose of the study that they went over in their text was to test whether nurses receiving an experimental treatment would differ in their level of stress from those who did not receive a treatment. So those that did not receive a treatment were in a control condition. So nurses were not randomized to experimental or control groups at the individual level. Rather, the wards were randomly assigned to the treatment or control condition. So basically all nurses within a given ward received the same condition. Now in terms of the variables, at level 1 the outcome variable was stress. The level 1 predictors included gender, which was coded 0 for male, 1 for female, age in years, and experience in years. The level 2 predictors included experimental condition, originally coded 0 for control and 1 for experimental, but the authors subsequently grand mean centered that variable at level 2. And then they had ward type at level 2, which was coded 0 for general care and 1 for special care. The level 3 predictors included hospital size, which was coded 1 for small, 2 for medium, and 3 for large. And this variable was subsequently centered at the grand mean of the hospitals at level 3. And I know some folks are asking why didn't they treat this variable as a factor variable instead of a continuous variable, and that's just kind of how it appears in the demonstration, so I'm going to leave it that way to remain consistent with the presentation in the book. So now let's go ahead and look at the SPSS data file. So there are basically there's data on 1,000 nurses, and again those nurses are not nested within wards, which are nested within hospitals. So there are 1,000 rows of data. Each nurse in this data set has a stress score. So that stress score, or that stress variable, is the dependent variable in the analysis. The hospital variable that you see right here, this is the hospital level identifier variable, and then this ward variable right here is identifying the ward within hospitals. So keep in mind that because we have a three-level model, we need to be able to identify those level 3 and level 2 units. So hospital again is referring to the level 3 units, ward is reflecting to the level 2 units. And the ward variable, by the way, is set up to where it's reflecting or it's identifying the ward within a given hospital. There's actually this ward ID variable that you see right here that also identifies each ward, but it is a general indicator of ward across all of the wards within the study, and so the authors actually chose to go with this ward variable instead. My guess is because it kind of expedites processing time and makes things a little easier to generate the results. So at any rate, our level 1 predictors include age, there's gender, and there's the experience variable. Our level 2 predictors included the ward type variable and experimental condition right here, and then the level 3 predictor is hospital size. But just kind of refresh you, the experimental condition variable was centered right here, and then the hospital size variable that was also centered. Okay, so now that we've gone over our variables and the scenario, let's go ahead and begin by running our first analysis. So the first analysis in the PowerPoint is essentially testing a null model where we're allowing the intercepts to randomly vary across wards and across hospitals. So in that model, though, there will be no predictors that are included. So what we'll do is we're going to go to Analyze, we'll go down to Mixed Models, and then go down to Linear, and we'll move the ID hospital variable over to the subjects box and the ward variable over to the subjects box as well. So we'll click on Continue, and then the next step is to move our dependent variable stress over to the dependent variable box. Now under Fixed right here, this is where you typically are going to add in predictor variables. We have none for this first model. The only thing that I'll point out is down here it says include intercept, and that should remain clicked as it is right here. So there's nothing really to do with this particular box at this point. When we click on random, this is where we allow or add in random effects to our model. So again, we're going to be allowing intercepts to randomly vary within hospitals and across hospitals. So we'll start off by clicking on hospital and moving that over to the combinations box, and we'll include intercept right here. Then we'll click on next, and then we will select both ID hospital, ID ward right here, move them over to the combinations box, and click on include intercept right here. So next we'll click on Continue, and then we'll go to Estimation. So the default in SPSS in terms of estimation is REML, or Restricted Maximum Likelihood Estimation, and this is typically best used in those cases where you have a smaller sample size at the higher levels for your model. And just to kind of keep ourselves consistent with the presentation in the Hawks et al. Text, we're going to stick with their estimation approach. They use maximum likelihood, so we're going to select that, and we're also going to go down here to residual method because I'm trying to kind of replicate exactly what their results. So we'll click on Continue, and then we'll click on Statistics right here. And next we're going to, there are various options available to you. I'm going to select parameter estimates for fixed effects, test for covariance parameters, and then I'm also going to go ahead and select covariances of random effects, although this is not going to be useful at this point. I'm just going to leave that default clicked for later on. So we'll click on Continue right here, and then we'll click OK to generate our output. So you'll see the first table, the model dimension table, just gives you a general overview of the model and what parameters are being estimated for that particular model. And you can see with this that basically we have one fixed effect, which is essentially going to be our intercept for the model. And then you can also see that we've got two variances that are being estimated. Essentially the variance of the intercept at the level 3 and then at level 2 right here. So that gives us essentially three levels, or three parameters are being estimated right there. And then there's also one additional variance estimate, which is at level 1. And actually, to tell you the truth, I really should have probably highlighted this column right here. So I'm sorry about that. So anyway, there's our fixed effect for the intercept, the variance at the hospital level, variance at level 2 right there, and there's the level 1 residual variance being estimated. So that's going to produce 4 parameters that are being estimated within the model. We'll scroll down a little bit. You'll see that there's this box containing information criteria. We're not really going to be going into this particular topic within this video. Like I said, there's a lot of moving parts that we're working with, so I'm trying to keep this as simple as possible. If you want to read up more on what this information is and so forth, you can certainly check out that Hawks et al. Text for more description. So at any rate, with respect to our fixed effects, like I said, the only fixed effect in our model is that for the intercept. So essentially this would be the grand mean of stress responses across the hospitals. So that you could think about it as the expected level of stress for an individual randomly selected from Ward J within Hospital K, if that's the if you want to kind of think about it from that kind of standpoint. You'll notice that there is a significance test that's provided, and quite frankly, it's oftentimes not utilized in the context of interpreting the intercept. And the reason why is because it's essentially a test of whether the intercept is significantly different from 0, and that's just oftentimes not of substantive interest. So we oftentimes just kind of ignore that particular bit of information. And so we'll scroll down a little bit further, and you can see that in the covariance parameters box we've got the remaining 3 parameters that are estimated. So this column right here contains estimate of the level 1 residual variance. So this is the level 1 residual variance right here. Then we have down here the level 3 residual variance that you see right here, and then we've got the level 2 residual variance right here. So you'll notice that we have a significance test associated with each of those variance estimates. So if you take the estimate and divide by the standard error, you can basically carry out a walled z-test that's given right here, and you've got a p-value over here. So you can use these significance tests to make determinations about the level of clustering going on at different levels. So I do kind of talk a little bit about this in a bit more detail within the PowerPoint, an alternative approach to kind of testing significance of the level 2, level 3 intercepts would be using a likelihood ratio test. I don't actually demonstrate that in the PowerPoint, and I'm not going to do that here because it involves kind of going down another rabbit hole, but that is an alternative approach that you might consider when you're testing variance components. But nevertheless, we're going to use a p-value that's actually half of each of these p-values that are printed out when it comes to interpreting whether we have statistical significance. So in that particular case, you can see that the level 3 p-value, we can just continue to say that the variance, the p-value for the test of the variance or across wards, if you will, is less than 0.001. At level 1, that variance is also statistically significant. And then at level 3, that p-value will be 0.0285. So that's just basically half of this number that's given right there. So we have significant variation in the level 1 residuals, and then also significant variation in the variance components at levels 2 and 3. And before I move on, just keep in mind in that PowerPoint for this particular demonstration, I also show you how you can compute the intraclass correlation coefficient associated with levels 2 and 3. And well, here's just a slide right here from that PowerPoint, and you can see that basically what we're going to do is take the variance estimates from levels 1, 2, and 3. So basically taking all 3 of these numbers right here, adding them together. That's in the denominator of our formula, and then dividing it by by the variance component that we're interested in. So the ICC at level 3 is just basically computed by taking the 0.162 right here and dividing it by the sum of all 3 of those variance components. With respect to the ICC at level 2, we would be taking the 0.488 or 8, or we'll just round off to 0.489, taking a ratio of that variance right there to the sum of all the remaining variances. And then, by the way, if you wanted to figure out the proportion of variation still remaining at level 1, that's easily done just by taking the 0.301 that we have right here and then dividing it by the sum of all three of those variance estimates. Okay, so the next thing that we're going to do, or the next model that they tested in their chapter, was including all of the predictors from levels 1 through 3. So what we'll do at this point is go into Analyze, Mixed Models again, Linear, and we'll keep all the previous settings, but in this case now we're going to start moving our predictors over to the covariates box. So you'll see we have nurse age in years right here, there's gender, we have nurse experience right here, we also have type of ward, so I'll move that over right there. Now the hospital size and the experimental versus control condition, both of those, they use the centered versions of those variables. So I'm going to go down to the end of the data set here, and there's the centered experimental control variable and then the centered hospital size variable right there. So we'll click Fixed, and we'll kind of use this little down arrow and go down to Main Effects right here, and we'll select all of our predictors and click on Add. So just keep in mind that, again, these models are very complex. Theoretically, we could have gone through a series of models where we added in, say, level 1 predictors and then moved on to adding in level 2 and then level 3 and so forth. But again, we're kind of sticking with that demonstration in their text, and for that second model that we have right here, we're essentially adding all of those predictors all at once. So just kind of keep in mind that this, the strategy that's being reflected right here in terms of what models to add and which parameters to allow to vary and so forth, that is not necessarily set in stone. It just kind of reflects a set of decisions for entry of certain parameters at different points. So at any rate, we're going to click on Continue right here, and then under Random, you'll notice that we're essentially just going to leave everything as is. So we're just going to leave well, everything as is. We're not going to do anything else with that. We're just going to leave the fixed variables in there, or fixed effects in there, and everything else in terms of our selections, we're also going to leave the same. So now we'll click on OK, and you'll see that now our model dimension tables just seems to kind of blow up in terms of its size right here. So you'll notice that now, in terms of the parameters that are being estimated, we still have that intercept parameter that's estimated for the fixed effect. We also have the regression slopes for each of those individual predictors that we've included in our model. We still have the variance estimates at levels 3 and 2 right here, and then also at level 1. So when you sum all those parameters up, that gets us 10 parameters that are being estimated for the model. When we scroll down now, we can look at our estimates of fixed effects, and you'll see just kind of generally as we go through that you see that age right here, it has a positive regression slope, and you can see it's statistically significant. So given that that age variable has a positive slope, that would actually be an indicator that folks who are older, or nurses who are older, tended to have greater stress. The gender variable right here that you see has a negative regression slope, and you got to kind of keep in mind the coding associated with gender. Remember that it was coded 0 for male and 1 for female. And given that negative regression slope that you see right there is basically indicating that females had lower stress than males. And you can see that the difference between those two groups is statistically significant. Then we have experience right here, and you can see that there's a negative regression slope right here, and you also see there's significance. And that negative slope is basically indicating that nurses with more experience are experiencing less stress. With respect to ward type right here, you can see that there's no significant difference between the types of wards in terms of their levels of stress. When we look at the centered experimental control variable that you see right here, you can see that we have a negative regression slope and you can see that it is statistically significant. Just keep in mind the original coding scheme before centering basically just has the higher, it was coded 0 for control group, 1 for the experimental group, and then following coding it's basically a negative 0.5 for the control group and 0.5 for the experimental group, at least as I'm kind of looking, as I just kind of looked at the data set and looked at the way it was set up. So at any rate, given that the higher number in terms of the coding is reflecting the experimental condition, that negative regression slope that you see right here is indicating that essentially wards receiving the experimental treatment experienced less stress than wards that were in the control condition. So then when we look at the hospital size variable right here, you can see that we have a positive coefficient and we have statistical significance. So that's basically telling us that hospitals that were larger in size tended to have greater levels of stress. When we scroll down to the estimates of covariance parameters right here, you can see that our level 1 estimated variance right here, you can see that we have statistical significance, and then you can see again at the ward level right here, that variance estimate, we have statistical significance, and then at the hospital level we also have statistical significance. We just want to make sure that when we're reporting we would divide that p-value in half to report on that. So next up, we are going to allow the effect of experimental versus control condition on stress levels at the ward level to vary across hospitals. So in other words, the effect of being in a treatment or control condition, in this case we're going to assume, or at least allow for the possibility that those effects are not the same across all hospitals, but in fact perhaps the differences that you would observe vary across hospitals. So to do that, or to allow this to occur, we're going to have to allow the slope for our experimental control variable to randomly vary across hospitals. So we're going to go to Analyze Mixed Models again, go down to Linear, Continue, and then where it says Random, now what we're going to do is we're going to kind of go back to where it says Previous right here, because we want to allow the effect to vary across hospitals. So in this case we're going to click on the CEXP variable, that's our centered experimental control variable right here, and we're going to move it over to this box on the right. So again, we're only looking to see how this effect at level 2 varies across hospital, which is our level 3 unit. So we'll click on Continue, and there's nothing else. Oh, actually one other thing that we might want to do, sorry about that, while we're under this, is because we're allowing the slopes and intercepts to randomly vary, we might also want to allow for the possibility of a covariance between the randomly varying intercepts and slopes. So to accomplish that, we can click on Covariance Type and go down to where it says Unstructured, and so this will allow an estimate of the variance of the intercepts, variance of the slopes, and then also the covariance between the intercepts and the slopes. So we'll click on Continue and then on OK to generate our output. And so you can see once again we've added yet another parameter to our model, and that is, in this case right here, we're allowing we're adding a couple of more parameters to our model. So in our previous model, only the intercept was randomly varying. So in this model, we're adding in a random variance, or variance for the randomly varying slopes, and then also the covariance. So in the previous model, we had 10 parameters that were being estimated. Now we're up to 12 right here. So we'll scroll on down, and with respect to our estimates of fixed effects, basically there's no substantive difference in terms of how you would interpret the direction of the effects or the significance levels. So those are all the same, even though some of the values are different from what we saw before. So I'm going to scroll on down a little bit further, and you can see that in our table of covariance parameters, you'll see this is our level 1 residual right there. So that's at level 1. There's our variance estimate. You can see that we have significance. Then you can see that at the ward level, we have our variance estimate right here, and we have statistical significance. And then you can see our variation across hospitals. So you can see right here, this right here would be the variance of the intercepts. So there's our variance estimate, and we see that we have statistical significance. Then we have right here, we've got our slope variance estimate right there, and you can see that we have statistical significance. So that's telling us that the relationship between the experimental control variable and stress at the ward level is varying across the hospitals. So given that, we're probably going to want to model possible predictors of that randomly varying slope or the random variation in the slopes. You'll see right here the UN21, and UN is just referring to unstructured covariance matrix. So the one that you see right here, the 1,1 is referring to the variance of the intercepts. The 2,2 is referring to the variance of the slopes, and then the 2,1 is the covariance between the intercepts and the slopes. And you can see right there that that is actually not statistically significant. So we could theoretically decide to kind of take that parameter out and just kind of estimate the variances of the intercepts and slopes, rather than also estimating that additional parameter in terms of that covariance. But again, we're sticking with the demonstration in the text, and I gathered that they basically just kind of left that parameter in the final model that we're going to be estimating next. So for our last model, we are going to be adding in a predictor at level 3 of the variation in the slopes. And the only predictor that we have actually at level 3 is that hospital size variable. So keep in mind that because, again, we saw variation in the slopes, or significant variation in the slopes for the effect of the treatment variable on ward level stress, if you will, then with that variation across the hospitals, we might have some kind of hospital level characteristics that may explain that variation in the slopes. And so because of that, we're going to be modeling a cross-level interaction. So to do that, we're going to go to Analyze, go to Mixed Models, click on Linear, and go back through everything. Everything up to this point is exactly the same. The only difference now is we're going to click on this Fix button right here, and we're going to add an interaction term. So we're going to click on interaction, and then we're going to click on our two variables that we are interacting. So we have hospital size at level 3 and our centered experimental control variable at level 2. And so when we highlight both of those, we'll click on add, and so that interaction is going to be added as a fixed effect within our model. So we'll click on continue and then on OK, and we'll generate our final set of results. So you'll notice that we've added one additional parameter to our model right there. So now we're up to 13 parameters that are being estimated. We'll scroll down, and we can see that we have in our table of fixed effects, we now have this interaction effect that's given right here, or the interaction term. There's our regression slope, and you can see that we have statistical significance. So what that's basically telling us then is that that relationship between the experimental control variable at level 2 and the ward level stress, if you will, that relationship is being moderated by hospital size. Now, typically, after you find something, a significant interaction effect, you might want to plot out that interaction effect, or carry out some types of simple slopes tests. And unfortunately, SPSS just does not have that mechanism or that capability in the basic program right here. So I will say that if you want to kind of further unpack that interaction, kind of describing what's going on, one option would be to use kind of an online calculator that Chris Preacher has come up with that would allow you to kind of further probe the nature of that interaction. And in the PowerPoint, I do include a link to that right here. It's kind of towards the end of the PowerPoint. But that said, I know oftentimes people would like to hear a little bit more of the story, or maybe not. I don't know. But at any rate, what I did do was to kind of use an approach to compute the simple slopes for the effect of the experimental condition variable on the ward level stress at different levels of the hospital size variable. And so just kind of keep in mind that because the hospital size variable was centered at its mean, and also we had our centered experimental variable as well, but because we've centered our two variables right here, we can interpret the effect right here for the centered experimental control variable right here as the difference between those groups for hospitals that are average in size. So that's kind of how you can think about what that particular coefficient is. It's just simply a simple slope of the effect of that particular variable at the mean, again, because we've centered that hospital size variable. And so that that tells you right there that there is a difference between stress levels between the treatment and control conditions, and that this difference right here is reflected at the mean of the hospital size variable. Now in the PowerPoint, I was able to take that information from the regression slope for our experimental control variable and the interaction term, and also computed the standard deviation for hospital size at level 3. So with that information, I was actually able to compute the predicted slope for the effect of the experimental control variable at one standard deviation below the mean on the hospital size variable and one standard deviation above the mean on that variable. So when I did that, what we ended up with is a slope of negative 1.204 at one standard deviation below the mean on the hospital size variable, and that one standard deviation above the mean, it was about 0.207. So you can see basically as we move from smaller hospitals to larger hospitals, that the slope changes from the most negative of negative 1.204 to the negative 0.499 at the mean, and then to 0.207. So the slope is becoming less negative and basically increasingly positive. And essentially what that's kind of telling me, particularly given the values at the mean and one standard deviation below the mean on that hospital size variable, is telling me that as hospitals size increases, the difference in the treatment effect appears to be becoming weaker. So in a nutshell, the effect of the treatment variable on ward level stress appears to be strongest with the smaller hospitals. Okay, so that is going to pretty much wrap up this video presentation with respect to three-level, multi-level models using SPSS. Like I said, there's a whole lot of different elements to these types of models, and I could really only scratch the surface in this presentation. But I do hope that you found it useful. Again, I encourage you to download a copy of the PowerPoint. Every once in a while, by the way, I do go through and kind of update the PowerPoints or whatever, and try to kind of clean things up a bit. So if it happens to be, maybe check back periodically and just make sure that that there's no recent edits, if you will. So that again concludes this video presentation. Thank you again for watching.